Hello. In this video, we will be discussing some examples of the previous discussion on vector notations, unit vector, vector and vector operations. So let's take this first example. Example 1.1.1. Determine the vector R12 directed from point P1, which is at 4, 1, negative 1, to another point P2, 0, 3, 0 in rectangular coordinates, and also determine its unit vector. So to solve this one first, we need to plot the vector so that we can see the vector itself. So this is a plot. Try to plot this one in my online plotter. So the blue ones, blue vectors here, the vectors that coming from the origin towards the point, they are called the position vectors. This is what we call the position vectors. The two types of vectors, position and directed vectors. While R12 here, that's what we want to solve or calculate or determine. That is called the directed vector. It's from point 1 to point 2. So to determine R12 is just equal to the difference. It's just equal to the difference of the position vector, which is R1 minus R2. So if we determine what is R1, R2, then we subtract the two vectors, and that will be our R12. So what will be our R1? Position vector R1. So this is a vector R. This is also a vector R1. R1 has components 4 AX because it's a position vector plus 1 AY and a negative, so minus AZ. So this is R1. For R2, position vector, this is just equal to 0 AX, 3 AY, and there's no component at the Z direction, so it's just 3 AY. And if we want to solve for R12, we just need to subtract that. And based from our previous discussion, the operation of vectors, we can subtract them. We can only add or subtract vectors that have the same direction, or in other words, we can also add or subtract the components of the vectors in each component. So here, in R1, we have 4ax ay minus az, while in R2, we don't have any component in ax, we only have a component in ay, and we don't have a component in az. So we just add this one or subtract this one. So 4ax plus ay minus az, we just subtract minus 3ay. So R12 now will be equal to 4ax, then this one, 1 minus 3, that's actually equal to negative 2 ay, then minus az. So this is now our directed vector from 1.1 P1 to P2. And the other question here is we also want to determine its unit vector. So how do we again determine the unit vector? Using our formula before, unit vector is equal to AR12. This is the unit vector of R12. This is just equal to the vector itself. You divide it with its magnitude. R12, the magnitude of that vector. And how do we calculate the magnitude? For AX minus 2AY minus AZ, we just take the square root of the sum of the square of the components. So 4 squared plus 2 squared, then plus 1 squared. So therefore, AR12, or the unit vector of vector R12 is just equal to square root of 4 squared, 1 over square root of 21. We can factor out that, and you multiply this with 4ax minus 2ay minus az. So this is now the unit vector of vector R12. So that's how we determine directed vector from position vector. So we just subtract R1 minus R2. Then next example here. If another vector, we have a vector A, which is equal to 2ax plus 3ay minus 5az, and another vector B, which is equal to ax minus 2az. And we want to determine r, which is equal to a plus b. So these are all vectors. And also, we want to determine the magnitude of r and also the unit vector of r. So solution. So we just add this one. So it's the separation of a vector. So r vector is this equal to a plus b. Our a is 2ax. 2ax plus 3ay. Then we have minus 5az. Then this is our a. We add this with the vector b, which is ax minus 2az. Then we add the components individually. So r now will be equal to 2ax plus 1ax. That's just 3ax. 3ay. We don't have ay here, so it's just 3ay. Then minus 5az minus 2az is negative 7az. 7az. And this is now our vector r. Then for the magnitude of r, and again, this is equal to the square root of 3 squared plus 3 squared plus 7 squared. And this is actually equal to the square root of 67. For the unit vector, applying again the formula for a unit vector, ar will be equal to r over r, 3ax plus 3ay minus 7az. 7az, you divide this is the vector itself divided by the magnitude, which is square root of 67. And we can distribute the square root of 67, unlike what we did in the previous example. So we can make this one as 3 square root of 67ax plus 3 over square root of 67ay and minus 7 over square root of 67az. So this is now the unit vector of the vector r. Next, another example. This time, we're given a vector field. So a vector field is, it's just like similar with in two-dimensional, we have functions, equations, functions. If you have values for x, you get the value for the function f of x. Here in vector analysis, vector field can also be considered the functions. This is like a function in terms of x, y, and z, but in three-dimensional. So we can just input values for x, y, and z. So instead of just one value, we input 3 values to determine the actual value of the vector at a specific point. So let's try this. The solution. If we are given a vector field E, so the first thing we need to do is to determine the value of the vector or the vector in that given point. So determine the projection of a vector at 1, 2, 2 on vector f equals 4ax minus 3ay. This is a very good example. This is an application of the dot product. This is a very good example of the application of a dot product. And that product are used. That product is used to determine the projection. It's the other term for the dot product. When we say projection, so for example, if we have here a vector A, if this is vector A, then we have another vector at this point. Let's call it vector B. And that vector B has a unit vector A, B. Now, if we take the dot product between A and that unit vector AB, if they have an angle here, angle theta, then what we are getting is actually this projection. This length here, from here to here, is actually equal to that A, and you take it, the dot it with that unit vector AB. So another formula for this one, because AB is equal to B divided by the magnitude, so this is a vector, so we can also say that this is also A dot B divided by the magnitude of B, because vector B divided by its magnitude is actually AB. That's the unit vector. So another formula for that, or you just simply dot the vector A to the unit vector AB. So in this example, this one should be E. And we want to determine its projection on vector F. So the first thing that we need to do, so this is what we want. We want to determine this length here, from here to here. So this is the projection of E on F. So how do we determine that? That's just equal to that E, and we take the dot product with the unit vector of vector F. We can call it AF. AF. So to do this one, first we need to determine E at that given point. Because this is a field, we need to determine the actual vector at that field, at that point. We're at 1, 2, 2. So your x here is 1, your y is 2, and your z is 2. So we just need to substitute this into the vector field. So we have a y minus 1, or 2 minus 1 in ax, plus 2 times x. Our x is 1, so 2 times 1 ay, then plus 3 az. So the vector E will be equal to 2 minus 1 is 1 ax plus, or this is minus 2. Should be minus 2 ay, then plus 3 az. So we now know the vector E at point 1, 2, 2. Next, we need to determine AF. How do we determine AF? AF is just equal to the vector F divided by its magnitude F. So we can substitute this one into that equation. So we have now the projection of E on F will be equal to this one, AX minus 2y, 2ay, plus 3az, so this is E. Then we take the dot product with F. What is F? F is given 4ax minus 3ay. So this is 4ax minus 3ay. And we divide this with the magnitude of F, which is equal to the square root of 4 squared plus 3 squared. And 4 squared plus 3 squared is equal to 5. Then you take the dot product. By using the definition of dot product, what's the definition? We just multiply each component, the same component of the vectors. So for example, here, AX, X component, in the first vector, the X component is 1. So this is 1 times 4. At the other vector is 4. Then, next, we add with the Y component, negative 2. At E and at F, it's negative 3. So this is negative 2 times negative 3. Then lastly, plus for AZ, 3 at the other side, at the other vector, we don't have a Z component. That means the Z component is 0. So 3 times 0. Then we divide this with square root of 4 squared plus 3 squared. So this is now the projection. If we compute this one, 1 times 4 is 4 plus 2 times 3 is 6. 6 plus 4 is 10 divided by 5. It's equal to 2. So therefore, the projection of E on F is now equal to 2 units. So that length is just equal to 2. So this is one of the significant application of a dot product. Next, so this will be our last example. So for our last example, calculate the smaller angle between the vectors A, which is equal to 3ax plus ay minus 2az, and another vector B, which is equal to ax 3 minus 3az, by using that product and by using the cross product. So we use the 2. Let's start first using the dot product. Dot product. So remember our definition of a dot product. So if you have two vectors, A and B, if you take the dot, the definition of dot, this is equal to the magnitude of A multiplied by the magnitude of B, and you multiply it with the cosine of the angle between them, the smaller angle between them, which is what we want, this theta here. That's the unknown in the problem. Calculate the smaller angle between those two vectors. So the first thing that we need to do is to find what is the dot product of the two by using again the definition, the other definition, the one that we use here. We multiply the components. So A dot B now, A dot B will be equal to, because for X components we have 3, for B we have 1, so 3 times 1. For A, again in Y component, so plus 1. Then for B, it has no Y component, so you multiply it by 0. Then lastly, for the Z component of A, it's negative 2. You multiply it with the Z component of B, which is negative 3. Then we compute this one, 3 plus 0 plus 2 times 3, 6. 6 plus 3, this is equal to 9. Then we substitute this one in this equation here. But before we do that, first, what is A? The magnitude of A. That is just equal to the square root of A, 3 squared plus 1 squared plus 2 squared. This is equal to 9 plus 1, then plus 2 squared plus 4. And that is equal to the square root of 14. Square root of 14. For B, magnitude of B is equal to the square root of 1 squared plus 3 squared. This is just 1 plus 9, square root of 10. Now we have the magnitudes, we have the dot product. We can now substitute this to solve for theta. So 9, which is the dot product, is equal to the magnitude of A, which is square root of 14. You multiply it with the magnitude of B, which is square root of 10. Then you multiply it again with the cosine of the angle between them. And we want to determine this theta here. So cosine theta will be equal to 9 divided by 14, square root of 140. And theta will be equal to the cosine inverse of 9 over 140, square root of 140. And if you calculate this in degree, the answer will be 40.48 degrees. So this is the smaller angle between the vectors A and B by using that product. We can also use the cross product to calculate the angle. So let's try it using cross product. So let's review what will be the cross product, the definition of the cross product between two vectors. This is the magnitude of A times the magnitude of B, and multiply instead of cosine, this is sine of theta, which is the angle between them. But we don't need the direction or the unit vector for this one. We want the magnitude of the cross product. So we can also do that so that we can remove the unit vector. We just want the magnitude. And after that, we already determined or calculated the magnitude of A and B. So what we do next is to determine this value here. It's also a scalar quantity because it's the magnitude. So first, determine A cross B. A cross B. So without using the formula, we can use the determinant method that we also discussed. So using the determinant method, we have AX, AY, and AZ. Then first, what's the vector? The first vector will be A. So be careful with the arrangement. Whatever comes first should be also here first to be written. So A is 3, 1, and negative 2. So this is 3, 1, and negative 2. Then we have another one for B. B is 1. We don't have y. So 1, 0, and negative 3. 1, 0, 0, and negative 3. Then to compute the determinant, we can copy the first two columns, 3, 1, EY, 1, 0. Then all downwards are positive. So these are positive. All upwards are negative. Minus, minus, minus. So this will be, for the positive ones, we have ax times 1 times negative 3. So that's negative 3ax. Then here, we have ay times negative 2 times 1. So that's negative 2ay. And here, we have az times 3 times 0, or that's just equal to 0. That's the positive values. For the negative, so minus 1 times az. So that's az. Then we have 0 times negative 2 times ax is 0. Then negative 3 times 3 is negative 9 times ay. Negative minus 9 ay. Then we can add this. So we have, there's no ax here, so this is negative 3ax. Negative 2ay. Then minus negative 9. Negative 2 minus negative 9 is positive 7ay. Then lastly, we have minus az. This is the cross product. But we want the magnitude of this. So how do we solve for the magnitude? So cross b. So this is just equal to the square root of 3 squared plus 7 squared plus 1 squared. And the magnitude is equal to 9 plus 49 plus 1. That is plus 10, so square root of 59. Then we know the magnitude of a cross b. We can substitute it here. So we have square root of 59 equals a. The magnitude of a, we already solved this. Square root of 14 and square root of 10. You multiply that. That is just equal to square root of 140. Then we multiply sine theta. Then solve for theta. Sine theta now will be equal to the square root of 59 all over square root of 140. So theta is the sine inverse of the square root of 59 all over square root of 140. So calculate this. The answer for theta is also the same, 40.48 degrees. 40.48 degrees. So this is cross product. This is how we take the cross product between two vectors. We can use this one, or you can memorize the formula. It's better to use this one. So this is our example for the vector notations and vector operations.